flood. Forward. The first concept here is the call packing. What is call packing? While we have a certain number of uh, trunks available within a system, what we try is to pack the usage of those trunks to the initial trunks. We are supposing that we are supposing that we are using a sequential search system. It is not a random search system. It means that if a new call comes in, then the allocation of the uh, trunk is not made like first it is given the first trunk, then seventh trunk, then fifth trunk, then 10th trunk. It's not like that. What we are trying to do is to maintain the sequence from 1 to 10. And not only that we are trying to maintain the sequence, we are also trying to keep the calls within the earliest numbers. For example, if one of the calls in that was running on an earlier number, for example, first, second, or third trunk, it is dropped or it has ended, then a new call, a fourth call would be allocated one of those three uh, links or trunks which are available, and it will not be given the fourth number of trunk or the fifth number of trunk. So we like to keep it tightly packed on the earlier numbers. But as the number of calls increases, for example, as we have already discussed that coming of a new call is a random process, and we do not know, and coming of the call is a random process, and the ending of a call is a random process. So we consider that once a call, if it is concluded, then the system rearranges itself. If it rearranges itself and it keeps the call packing to the earlier numbers, then it would be called a rearrangeable network. But the point is that we want to maintain call packing to the earlier numbers of the sequence. Now, what is a rearrangeable network? A rearrangeable network is basically a network that maintains an algorithm that ensures that uh, calls calls are packed to the earlier numbers of the trunks. We do not allow it to go beyond the earlier numbers if if an earlier trunk is free. For example, uh, if it is a system that manages to maintain call packing requirement, then we will call it a rearrangeable network. Now let's see what is the benefit of a rearrangeable network. Rearrangeable network lets us uh, make a system that has lesser number of cross points. And how is that managed? It is managed uh, by using lesser number of secondary switches. We can uh, we want to have lesser number of cross points so that the overall cost of the system is reduced. or optimized at least. So if we have a certain intelligence in the system in which uh, the the call packing is maintained, then we can use um, the totally n number of small n number of secondary switches, and what we come up with is a wide sense non-blocking system, because we do not want to have a system that has a blocking to a certain to a larger extent. We need a system that has less amount of blocking. But in parallel with that, we need to have a system with lesser number um, of cross points. So we need to have a rearrangeable network. If we do have a rearrangeable network, then uh, we can use um, a system. We can use a system with the total number of secondary switches less than greater n or greater than n. We can make G2 greater than or equal to n. So it can be a little bit more also, but at least we should have small n number of secondary switches. But in this case also, zero blocking is not guaranteed by the structure, and it is called a wide sense non-blocking. If we compare it with a strict sense non-blocking network in which G2 is greater than or equal to 2n minus 1, we have a considerably lesser number of cross points, because the secondary stage would have two would have n number of cross points as compared to 2n minus 1. For example, if we have n equal to 5, so in case of a wide sense non-blocking network, we'll have only 5 secondary switches, while in case of a strict sense non-blocking network, we'll have 2n minus 1 number of secondary switches. This would definitely and considerably increase the number of cross points in the system if we use a strict sense non-blocking network. Uh, Non-blocking without the need of without the availability of rearrangement. uh, mm, if the network is non-blocking without the need of rearrangement, the network is said to be non-blocking in strict sense. But what would happen is that we'll have to employ more number of a larger number of cross points, which would be incorporated in the secondary stage, because the number of switches in the secondary stages would be considerably high. As I have already given you an example of n in case of wide sense non-blocking network, n is the small n is the number, primarily it is the number of inlets per primary switch, and it is also the number of outlets per tertiary switch. If we keep that value n as the number of secondary switches also, then we'll have a wide sense non-blocking system. While in this case, in the strict sense non-blocking system, it is the case in which rearrangement is not available. Algorithm for the rearrangement is not applied in the system. Then we'll have to employ larger number of secondary switches. And how much large that number is? It is 2n minus 1. So it is definitely larger than the wide sense non-blocking. Uh, Now, I would like you to see a number, a network in which a switching network in which we have n incoming trunks and n outgoing trunks, capital N incoming and capital N outgoing trunks, and if we have n minus 1 busy inlets per primary switch and n minus 1 busy outlets per tertiary switch, then one free inlet in one primary switch and one free outlet in one tertiary switch, uh, what would be the effect of such a system? We would require an additional switches on the secondary side, right? Now let's calculate the number of cross points in a three-stage network. The number of primary switches is definitely capital N over small n. Capital N is the total number of inlets from the primary side. Number of secondary switches, since it is a strict sense non-blocking system, that are 2n minus 1. And the number of tertiary switches is capital N over small n. The number of cross points per primary switch would be small n, which is the number of inlets per primary switch. Here it is. Let me mention. And we multiply it with 2n minus 1. What is 2n minus 1? 2n minus 1 is the number of secondary switches, and the number of secondary switches is also the number of outlets per primary switch. So n into 2n minus 1 is the total number of cross points in a primary switch. Number of cross points per secondary switch is n over small n whole square. It should be here basically. Let me clear it. And this is nothing. Right. Why it is capital N over small n square? Because capital N over small n is the number of primary switches, which is also the number of inlets per secondary switch. And capital N over small n is also the number of tertiary switches, which is also the number of outlets per secondary switch. So we multiply capital N over small n by capital N over small n, and we get the number of cross points per secondary switch. Now, number of cross points per tertiary switch, again, since the number of secondary switches is 2n minus 1, that is also the number of inlets per tertiary switch, and we multiply it with n, which is the number of outlets per tertiary switch. So now we have the numbers of cross points per primary and per secondary switch and per tertiary switch. Now to get the total number of cross points in this three-stage network, we need to have the cross points per stage. In the first stage, we have n into 2n minus 1 cross points per primary switch. We multiply it with the total number of primary switches, which is capital N over small n. Small n and small n are cancelled, so capital N into 2n minus 1 is the number of cross points per primary switch. The number of secondary switches is 2n minus 1, and if we multiply it with the number of cross points per secondary switch, which is capital N over small n, we get capital N over small n whole square into 2n minus 1. Similarly, the number of cross points per tertiary switch is 2n minus 1 into small n, and we multiply it with the number of tertiary switches, which is capital N over N. When we multiply it, small and small n are cancelled out, and we get capital N into 2n minus 1. When we add these up, we get C3, which is because each of these terms would have 2n minus 1, we get 2n minus 1 into 2n plus capital N over small n whole square. We differentiate it with respect to n and equate to 0. When we do in doing so, we get an equation 2 into small n cube plus capital N into small n plus n is equal to 0. We can put the value of small n we can put different values of small n. For example, we can put 2 and in this case capital N would be 16, and 16 would be satisfy this choice. If we choose n small n to be equal to 3, capital N would come out to be 27. But if we see from this equation that small n is very large, then what would happen, that this capital N part of this above equation, 2n cube minus n into small n plus capital N is equal to 0, the capital N part can be neglected. If we neglect it, we have 2n cube minus capital N into small n equal to 0. We can take out n as common, and in this case small n is as common. We are left with 2n square minus n is equal to 0, and small n would come out to be under root capital N over 2. If we put this value of under root n over 2 in the above equation for C3 that I am mentioning here, which was 2n minus 1 into 2n plus capital N over small n squared, we put small under root n over 2 in place of small n. We get this value of C3 is equal to 2 raised to power 5 by 2 n raised to power 3 by 2 minus 4n. For a network with large value of n, if we have a very large number, large value of n, for example, if the number of inlets or the number of outlets is very large, what should we do? Fewer cross points will be required if multiple stages are used. Instead of one stage or 3 stage, if we use 5 stages, that would be a better choice. If the secondary network is replaced with a level that itself consists of a 3-stage non-blocking network, we are just replacing the secondary network or the secondary stage with a complete 3-stage non-blocking network. It means that we would have 2n minus 1 levels of such switches, just like we had 2n minus 1 secondary switches in a 3-stage network. What we would get is a 5-stage network. In such a case, the number of cross points of C5 will be minimum when small n is equal to 2 into capital N raised to power 1 over 3. How do we get it? In the similar way as we have done in the earlier case, that we find out the number of switches in each case and add them up, we get C5, and after that we differentiate it with respect to small n and equate to 0. In this way we get the value of small n, which comes out to be 2 into capital N raised to power 1 over 3. We put that value in our initial equation of C5, and we get this value of 3 into 2 raised to power 7 by 3 into n raised to power 4 by 3 minus 14 n plus 2 raised to power 5 by 3 into n raised to power 2 by 3. This would be the shape of a strictly non-blocking 5-stage network. Similarly, we are putting n incoming in trunks and n outgoing trunks, and we have put, instead of a secondary stage, we have put complete three stage networks, each in place of each secondary switch, and we come up with a five stage network. Why do we go to a five stage network? We only go to a five stage network when the total number of incoming trunks and outgoing trunks is very large. Instead of 10 or 100 at the maximum, which we used in a three stage network, we come up with 1,000 incoming trunks and 1,000 outgoing trunks. In such a case, we need to have more stages, and five stage network is quite a good choice in this case. Here it is very clearly done. Example, you can see example 5.9. We have to design a strictly non-blocking network for 100 incoming and 100 outgoing trunks. We choose a three-stage network. Minimum number of cross points are obtained where small n is equal to under root capital N over 2. This we already have, and we come up with 7.07. In 7.07 is something in between, so we can take n equal to 5 and n is equal to 10. If we use n is equal to 5, the number of secondary switches would be 2n minus 1, which would be 9, and this is the case of strictly non-blocking network, since our example is demanding that. Total number of cross points is C3. We are just using that equation and that formula that we have already got. C3 is equal to 5400. We find that out. This is done in, you can see the resulting design is shown in this 5.20a. We are talking about the levels in between first and the fifth stage. Each level has 100 incoming and 100 outgoing links. Actually, we are talking about the that secondary part, which was actually the secondary part, but we replaced that switch with three stage level, and in each level we have 100 incoming and 100 outgoing links, because each level is connected to all the primary switches, and the number of primary switches is 100, so each level is connected to 100 primary switches, which means that we have got 100 links to on the primary side. Similarly, we have got 100 links on the secondary sides, or the one between this three stage level and the tertiary switches, or the fifth stage switches, and these 100 are between each secondary or the three stage network and the tertiary network. So the total number of cross points is C5, and we have just used that formula, and we come up with 1,40,600 such cross points. In practical systems, we can show this as this sectionalized switching network, in which different sections of switching are practically connected over here, are designed and introduced in a switching network, in a digital switching network. If we have a three-stage network of TST, time, space, time switch, and we need to accommodate 100,000 lines, how can we accommodate it with a TST? We use a time slot. We use a time slot interfaces with 512 time slots. 256 time slots for each even numbered and 256 for each odd numbered slots. Switch maps each 8-bit time slot to 16 bits. So the bit rate at each time slot interface is 256 into 16 into 8000 is equal to 32.768 megabits per second. On the space stage side, we take, for example, we have a 25 by 25 matrix, and so the capacity multiplier is 25. We multiply this 32.768 by 25, we get 8192 and 5 zeros of that, this much bits per second. We have to divide it by the bit rate of each voice channel, which is 8000 bits per second, and what we are left with is 102400 lines, which are catered, which is more than 100,000 lines capacity.